Okay, so let's start talk in the morning. Quickly, we can turn Peng Fei Guan from here and give a talk about the Weyl isometric embedding problem for general three-dimensional manifold.
Thank you. I want to thank Professor Yaw and Justin for inviting me here again. Was here actually in this building in the basement of Sun Center last fall. I gave a talk related to this problem, and now I want to. This talk actually is a continuation from last one, but there will be a few minutes of overlap, then we'll go to some more new results. Maybe I want to set the problem first. Now, suppose we have two-dimensional and compact Riemannian manifold, and then question, can we embed this into isometry to a three-dimensional ambient space? Of course, and in the first talk, Camille already mentioned this of the Weyl problem. My problem is of a G, want to embed it in R3. So, well, the problem, of course, can be reduced. So we are interested about a little different the things. We want to look at what is resistance of some smooth and we want to call this phi. This is a map we call F. This map we have this such kind of F, which belongs to C2 of R. So yes, Camaro talking more or less below 2 C2, then we are interested about above of 2. And so as we know, then the Weyl problem is solved, and due to effort of Levy, that's for the net case and the Nuremberg, and also for Gorat. That's 1930s, and those are the 1950s. So that's complete solved. And why the reason probably we are interested in is related to the work so-called quasi-local mass. And for example, the Brown-York mass, that's defined by 1/8 integration of H0 minus H of M. Suppose now you have omega, which M equal to the boundary of omega, and in the space like three-dimensional domain, that's in three-dimensional. And suppose now its Gauss curvature of the surface of coming from this metric is positive, then by Nuremberg solution, then you can embed this M as a convex surface field of R3, and that's of embedding of that. So here you have mean curvature of H related to the boundary of omega, and that's you have mean curvature of H0 called. And as mentioned in the first talk, this embedding is unique up to residual motion, therefore mean curvature is uniquely defined. Therefore, you do that, and the remark results by Xu and Tan, seeing that, and this is positive. And then afterwards, is Liu and Yaw. They define Liu Yaw's mass. Instead, they consider in embedding and into this one here. Then this time, look at the inequality space instead of an R3, and here, then you look total mass, then this also positive. They define that, then they prove this thing because so then the work we got. That's also the Mutal 1 and the Yao. Actually, Mutal got me interested in this problem, and they did systematic work related to this isometric embedding and this causal local mass. I will come back to their work later on, but just we will use some the work by Mutal and Yao and to do the regularity. But originally, then we want to have the existence of isometric embedding related to the local mass, but this time we want to use the estimate to help to prove the regularity, and then from there you can go to the differentiation. Okay, so now just recall what is last time the results I taught here. So the results last time is little and more general. Suppose now you have the AM, which is already isometric embedding into some ambient space of G bar. Suppose G bar is a warp bar space. And of course, then use Gauss, so then of course we have from this embedding we have the mean curvature. Second dimension coming from this embedding or immersion. Then the second phenomenon, sigma 2 of this sigma phenomenon form satisfies this scalar curvature minus the scalar curvature of ambient space, the embedding of x of 2 plus of reach of mu of x, and the mu is the normal of the surface. And assume this is larger than equal to 0. That's more or less degenerate ellipticity condition for any M. You even don't need to be of that. It's not necessary to assume this in so-called gamma 2 cone in guiding cone. But as long as this is no negative, and in any empty space you can embed it there in this with this warp buzzer space, then you have a bound. So mean curvature is bound. So this more or less, okay, now going back to there. So this, of course, is always a very boring process, but standard then to produce an isometric embedding is used so-called methods of continuity. So method continuity as it goes, there are 3 steps. The first step is you find the homotopy path. And let's call it M of 2 over G of T, such that G0 is embeddable. And of course, the second one then you want to prove then is openness, and third one is closeness. So that's the standard procedure to produce a solution for this isometric embedding. Well, now I want to go backwards. Okay, so now going back to this estimate we had before, but this estimate depends on geometry of the intrinsic geometry and the extrinsic geometry, plus the position of the embedding of x. Well, if in plus 1 is, say, space form, then that's not in general no problem, because you can always use rigid motion such that origin contained inside of the body. Therefore, because then this is bounded by the diameter, intrinsic diameter. So that is, But in the general Riemannian manifold, that's the problem. Because you do isometric and embedding use method continuity, you don't know when, even you curvature and control, things may drift apart, afar. You want to control, okay? So that's the main difficulty here. So what's missing is C0 estimate. So that depends on C0 estimate. So if and this is space form, that's no problem. C0 is automatic. Now you see then once you going to general space, that's the main difficulty for this isometric embedding. Okay, so now I want to go backwards, and then I'll discuss 3, then to point how to get the C0 estimate, and then I'll go to use that to understand openness problem, then the recent work. So now I'll underline that. So for this part, I want to discuss the recent work by my student of mine. That's this so-called ellipsis estimate, strict ellipsis. I will come back to state exactly what I mean. So that is 3 parts, and the second part, and then I use so-called recent work by Chen He Li and Zizhan Wang too. My postdoc was at McGill. That's now they are now finished. That's the openness and the no rigidity. Turns out no rigidity is very interesting. I will come back. That's related to the isometric and carbon inequality also. So these 2 things are mixed together. I want to emphasize that one is regularity estimate, other is some type of the geometric inequalities, combine the 2 together. So now we want to get C0 estimate. So now, well, C0, recall what we do then, of course, use method of continuity. Suppose now you do of this embedding, then suppose ST is the embedding for t time at t, and then you want to solve the linear system of that dx of d tau t that's equal to some q of t. That is the deformation vector field. That's for the openness, you have to solve linear system equation. So that's the equation you want to solve, system of linear equation for tau. But the result by Li and Wang is that the homogeneous equation, and that kernel is, the dimension of this kernel is exactly of 6. So that's, of course, in Euclidean space, that's fine, because you always can rotate. So that is, the rotation gives 3 dimension, and translation gives you another 3, so that's 6. So that's match. That's true for general Riemannian manifold. And moreover, they prove then for equation, I call this equation 1. They prove that this guy will have estimate less than equal to C. If this T is perpendicular to the kernel, maybe I call this kernel, equal to kernel of kappa. So this perpendicular to the kernel. And this C depends on the ellipticity of the second Feynman form. So, and that C depends on lambda. Here assume lambda ij larger than equal to lambda, and larger than equal to 1 over lambda. So now we are going on circle. Okay, so we start, this guy depends. Okay, once you have an estimate of H, then you get, if the curvature is positive, then you get estimate of all the eigenvalues or estimate of the second Feynman form. But now this depends on C0. So now you're going back to here, you have particular that you can find this guy on C, then of course, then from there, of course, xt can be integrated of x0 plus of tau t general. So you get, but this estimate also depends on C2 estimate. So now C2 depends C0, C0 depends on C2. That's the dilemma we have. Okay, so now let's go back to what's original and work by Nuremberg, and those three have different approaches. Levy instead of working on Mongeon pair, he translated Mongeon pair to a system of equations. Okay, elliptic type. Nuremberg estimate the equation directly use Mongeon pair. Pogorov is a little different approach coming from Alexander's original proof. Okay, so there are three different approaches. But it turns out that that approach by Levy was later used by Hans. Hans was able to prove the following here. So suppose we have isometric embedding embedded there. Hans estimates that suppose now if you of course in R3 also now I want to mention that in R3 everything can be translated to the double equation. Double equation can be translated to the Mongeon pair. Okay, so everything related to the Mongeon pair. To emphasize here then, we want to get away from Mongeon pair because you will see then in general it's not easy to write a Mongeon pair for Riemannian space because you don't know the normal is of C continuous in general. But in the space form, it is easy to prove normal is actually C alpha without much to do. That's related to Mongeon pair. So anyway, so that is so Hans find out the following way. So now locally then we have and I call the S theta square that's defined to be of maybe I just state things in Mongeon pair first, then things look easier, and then we'll discuss. And so suppose now you have an equation U11 and U122 minus U12 square equal to F is just positive. Okay. So now can define so-called U11. Okay, in the local coordinate now, the x square plus 1 square plus U12 dx1 dx2 plus U22 dx2 square. Of course, we assume this is positive definite, but we don't know the bound of U and J. But we know that it's positive definite. So therefore, let's more or less think about it as a metric. But in 2 dimensions, say suppose working on the disk, that metric of course can be written down as because conformal frac locally by monotonicity or uniformization theorem, you can write down as of and the form conformal and equivalent to the standard Euclidean R2 metric. So now he wants to explore the relationship between x and y. Okay. So what he finds then is following here. So x, you take the path of y with s variable equal to h1 of dy. Maybe I should. So now all the derivative will be with respect to y. Okay. And then maybe I should. So dx1 dx1 h2. Maybe I should eta y x1 dy1 d2 and plus of eta3 plus ds2 then you can write down that an eta4 that will be the Jacobi of dx and dy. You can write down. So that's quadratic. on the right-hand side quadratic, you can do the same thing for of x2. Then I will put the coefficients when and everything with tilde. And then he will able find that then eta 3 will be equal to 0 and equal to eta 1 tilde, that equal to eta 2 eta 1 tilde, eta 1 2, eta 2 minus, so that is okay, that's using this 2 plus tilde, that's equal to 0. So this coefficient is bounded, those coefficients are bounded, but this one have to be 0, but it was spread to 1, so on. They are special structure of that equation. That was he found. And then he was able to prove then if the solution, this of course is now and linear equation, but it is of nonlinear on the right hand, quadratic, so it's a little dangerous. Okay, so he needs to assume then of course that should be of W21. W21 then coming from, so W21, so this x belongs to W21, that's equivalent to say that the Laplace of U is bounded. It's easy to compute relationship. And also you can compute the relationship between the derivative of Uij with of these kind of derivatives. Okay, maybe I should write down this formula, then you will see. So that's just bypass almost everything the work of Nuremberg and Pogorov. That give you the direct proof. So relationship is then you can write on then U11 over the square root of f will be equal to operating of y x2 of square of Jacobi dx of dy and so on. So what he proved that this system of equation, I call this equation of 2, and has a C1 alpha estimate. So that means then what he proved then rating of gamma of x of C alpha is bounded. If metric is C3, you don't need a metric C4. Original proof of Pogorov and the Nuremberg is of C4. And then from there you can see here, then automatically this will be of C alpha. So you don't need this Avogadro and the Nuremberg and estimate from C2 to C2 alpha. That was originally was difficult there. So then you have all this estimate. So automatically you will imply then C2 alpha estimate. The catch here then f have to be bound from below. This estimate depends on lower bound of f. Of course, depends upper bound of f2. But as long as metric is the C3, then you have the C2 alpha. So that's Monge-Ampere. That can be applied to the Weyl's problem. So now for the general case, Riemannian case, and there is a problem. The problem here is then, first of all, equation will be much more complicated. And secondly, you don't know Laplace U will be bound. Here, because you know U is because convex, and then integral path give you then automatically Laplace U bounded. And also, so now the thing then to consider for general case, ambient space of N3 of G bar. What to consider is following here. So instead of consider of this, you consider of this of metric of the following. You just put of ij of dxi dxj. Use the second Riemann form instead of that. Put everything back to the Monge-Ampere. So just forget about Monge-Ampere. You just look at second form. So that is, and of course we assume HIG is positive definite, but a priori we don't know the lower bound and upper bound. So we want to get lower and upper bound. Use very similar idea. Again, this of course you can do the same thing because this again is a metric. If it's a metric, then you can also write down this as dy1 square plus dy2 all square. That part won't change. So now I want to discuss a little bit about space form case. For the space form, in this case, you can even do better. So now if N3 G bar is a space form, then instead of looking of this this Laplace with respect to y, because that's not very natural. It's natural for Mongeon pair, but geometrically not natural if you put Hij there. So natural one is looking of this form, dy over of square root of f dy. That's you should call it. F is coming from, so that here f determine of Hij equal to f. Okay, so now recall what we wrote down. F in general is equal to r minus r bar minus 2 divided 2 by reach of mu of mu. In the space form, those are constant. So that's only depend on x, independent on mu. Therefore, that f is nice. So then you can find out that a of x and satisfies equal to all those things and satisfies. And I will call this condition. So that is condition satisfies the condition, the C condition. Satisfies this condition. Okay, so now you want to ask, well, this modular few pages of computations, but you can do it. Just straightforward computation, you just write down the equation. In particular, if in space form, so if in space form, this actually equal to 0. That's why geometric and operator is better than standard Laplace. There are so many translations happen. So that's equal to 0. Because this here use the fact, key fact, that Hij is quadratic.
I don't quite understand. F depends on your embedding, right?
F depends on the embedding, yes.
So how do you write this equation?
So you assume embedded.
You assume already.
Yeah, you assume already embedded. Then we want to put here the proof regularity. So assume embedded. F is larger than equal to some C0, 0.
Okay.
So assume that, then we're going back to the prove the regularity. So here's the regularity part.
So you assume the axis is what, C0 embedding or C1, C2, whatever?
Assume the C3 embedding.
You assume
A priori.
Yeah, okay.
A priori. And then we want to get it as a bound a priori. Then going back to prove that actually C3 is bounded, non-bounded. So that is. So if this quadratic, then so many cancellation happen, it's 0. So therefore, automatically you can see here. And okay, so this kind of system of E2 can be generalized to of this kind of system, even with condition H under there, and that's it's have been generalized by many other people. So you can know it's kind of automated machine. Once you have condition satisfied, then putting there you get the C plus and the C1 alpha estimate. So once you have C1 alpha, and then Hij will be of C alpha. Therefore, then everything will be C2 alpha. So from C2 alpha, then go upwards is just standard elliptic theory, Schroeder theory. Okay, so that is, so it is equal to 0. And now, then one catch, because you want to have a solution start with W21. Okay, so solution start from W21, just same thing happens, then H and Ij divided by square root of f will be equal to relative of some. And so this can be bounded by, say, suppose now H11 can is in that coordinate that will be equal to x2 of square of gx dy, and so on. So now you want to have of this guy down to L1 integration. So for example, then same thing H2, 2 that's equal f equal to of y of x1 of square of Jacobi dx of dy. So those are the two equations. Middle one we really don't care. So now you multiply this Jacobi to the other side. Then you multiply Jacobi to the other side. Then you take a dy, and then that will be dy. dy time of Jacobi becomes dx. Okay, here for example, the Jacobi, you take a dy both sides. Well, dy I mean dy1, dy2. So then that will be dy1, dy2. dy1 dy2 times Jacobi, that's ds1, ds2. So in other words, to bound, you want to have this. This is bounded by in the y variable integration of y. That's equivalent to this is bounded in s variable. So that's equivalent to see that, and x cubed belong to w x belong to w21, and the equivalent to see then you take a trace the mean curvature operator. Whatever that's in s variable is bounded by some c. Well, now this kind of estimate, if in the space form, the standard that's coming from so-called Minkowski identity. In the space form, what we have here, then suppose now, in not just space form, more part space the same. So suppose now phi, recall g equal to g bar equal to of the r square phi of r square of the sigma s2. Now in 3 dimensions, so that's s2. Then the phi equal to integrate of r phi. Then because notice that this is killing field, the conformal killing field. Therefore, let's use key fact here, conformal killing field. Then this guy satisfies the following property. So in some sense, the divergence structure there. So now you compose one sigma 2 ij, that will become h, O n times h, then that becomes sigma 2. Sigma 2 is equal to f. So now you integrate this over, that's 0, because that's divergence free, and in space form is quadratic. So therefore, the integration of this guy equal to integration of this guy. In space form, you can always move, as we mentioned, the origin to inside. So this is bounded. And this guy is given bounded. Therefore, you get a bound of mean curvature integral. Okay, so that's space form. So in other words, the loose theorem 1 says that if g and g bar belong to C2 alpha, then and x embedding from S2 G into of a space form of N3 of space form will be of C2 alpha. Of course, it's a catch. Catch is that and R minus R bar of 2 plus mu is larger than some C0 larger than 0. And that's all estimate depends on this C0. So in some sense, it's a little improvement of hence, even in the R3, but in R3 case, it's already did by the Fermat shows. So the general form. So that's the thing. Of the simple model case. Now for general case, the general case, then we cannot do that because usually, first of all, you don't have all those kind of properties because in general, Riemannian manifolds you don't necessarily have properties. And also, very important here, this guy, even you have that, this guy may have a horizon. That's I want to discuss later. That may near zero. Near horizon, that's going to go zero. Therefore, you can even all those other things bounded, this may not be bounded. This is bounded, but doesn't mean mean coefficient be bounded. Because when approaching horizon, this goes to zero, H will be integration blow up. So that's, in general, this won't happen, and you don't know. But one catch here, then I want you, here we want to use, and the results are Wang and Yao, and also the Xu and the Tan. Okay. So Xu Tan did this positivity estimate for the quasi-local mass in the case of compared to R3. Then Wang Yao, and also let's denote this space kappa. Kappa is positive, larger than equal to 0. That's and the space form a constant, and the space form of curvature, section curvature equal to minus kappa. Kappa 0 is R3. So now what's the pro then? Suppose now and M to equal to bounded omega, which in some ambient space such that and section curvature of this ambient this is larger than equal to say actually they only need the scale curvature. So anyway, let's put the section curvature larger than equal to minus of some kappa. This you can always do. You can pick kappa curvature, of course, have a low bound because it's compact. And then two things. First of all, this omega section curvature of this here. Then also one want to have this and M2 symmetric of this guy is also larger than of this. So then what they prove is the inequality is following here. So then let H0 be the embedding H minus kappa, the embedding of this one to the space form. Okay, here in general domain, in Riemannian manifold. So compare with space form. So then that minus of H on the omega, and this guy is larger than equal to 0. So that was Wang Yao and combined Wang Yao and Xu Tan's result. Not explicit, but just straightforward directly from this here.
Not exactly this way.
I'm sorry?
It's not. The mean curvature of space-time is not a mean curvature.
Mean curvature of?
You're taking omega to be free
sorry.
But we are doing a space-time.
I think it's catch.
It's very different.
Sorry, I forgot the one thing. There's one term out here.
Well, okay. This one paper we did, but there's much more general.
Yeah, each general. We all need that. So this, anyway, so now in the space, then you can always put origin inside space form. You can always again put origin inside. This guy is bounded. So in other words, the mean curvature of this guy is bounded by mean curvature of this guy. But this guy, where the space form, we know that it's bounded by F. Okay, so that gives you the bound of mean curvature. So now from here, so then the second result of Lu's result here then if G bar belongs to C3, then the embedding of X C2 alpha 1 by C for all alpha between 0 and 1. But you don't catch 1. That's in general. But here, maybe I want to make a remark. In that proof, he went back to use Laplace instead of geometric Laplace. The reason he went back to Laplace is difficult to recall than the following here. So Laplace, of course, can straightforward computation, but in AO, recall that AO equal to, by definition, equal to y of term f depends on x, depends also on mu. Because in general, manifold is no trivial depends on mu. But in the theorem and in the ultimate machine, you have to assume that this guy, those things is C alpha. So in other words, you have to assume mu embedding in C1 alpha, then it's okay. But in the space form, automatically you can prove mu is C alpha. That you can prove. But in general, that's also difficult. But I think that's should be able to overcome anyway. So then should be low instead of C3, low to C2 alpha. So that's at least now, I think he's working on that. I hope this will be overcome later on. So now I want to come back to the second part, the openness. So I should have mentioned then, Pogrov has studied isometric embedding for general Riemannian manifolds, and he has established a series of results, openness and closeness, and so on. That's in his book. This green book, you can see that the chapter 5, 6, and 7, all three chapters devote to this kind of estimate. But if you look carefully somehow, you find then many things, and we still are not able to understand the few things. But in the space form case, it's general no problem. But many of other things coming from convex geometry in R3, automatically he assumed it's true in general Riemannian space. But that's probably at least some proof. But anyway, the approach is different. So that's the point. And also that the assumption also much weaker. So now I want to discuss the result of B and 1 for this local and openness. So then we are looking at this. So I want to solve this equation in more effective way. What they mentioned then, they found then this equation can always be solvable. And of course, a priori assume then ellipticity and constant, all solutions and bounds are dependent, and also dimension of kernel is 6. Therefore, then you want to ask, so what kind of rigidity results? So that's to solve the equation is one step, and one thing. To understand the geometry is another. So see if there is a rigidity. Then they prove then the following: there is no rigidity in general. So let's look at it in a general example. They will put example here. Then let's look at all this ambient space. G bar equal to d r square plus phi r square d sigma is 2. So here phi is just some function which is positive. So what do they prove the following here? So you look at the slice. So slice, suppose now the slice, let's call slice of C that equal to of R equal to C. Suppose slice should be very nice. Of course, slice is of course equivalent to of S2 of standard metric, but then just rescale by some certain kind of constant. This constant may be different, depends on phi. Maybe I just call the constant of C tilde. So it's a constant curve and round sphere. Okay, that's no problem. But now they do perturbation. So now you have a sphere embedded in a part in a three-dimensional ambient space. That is very nice. It's a slice of S of C. Now you do a little perturbation in the fixed one direction. Do a little perturbation, and you create a deformation vector field such that you can do the following way. Then the intrinsic metric. So then they were able to do of sigma c of epsilon. That's epsilon perturbation of the slice, such that the intrinsic metric G, that's exactly the same of intrinsic metric C of G. or if this in R3 or in space form by rigidity, then these are differed by a rigid motion. But they prove that that's not possible. So if at R equal to C, then this function of this R square at C minus phi of R, phi double of R, it's not equal to R equal to C, is not equal to 1. Okay, so now you have that is of C. That's the function of course the one variable radial function. The radial function, this guy is not equal to 1. Space form in Z is equal to 1. Space form, so space form, just recall space form here, then when it's a sign of R, other is of R, then that's the hyperbolic sign of R. So that's exactly equal to 1. But that's, suppose that's not equal to 1, just act of this here. Then that sequence of complete the same intrinsic metric, extrinsic is different. You cannot have a rigid motion in ambient space move one to other. Okay, so that is of this one here. So now I want to go back to this. So it turns out then, if phi of R square minus phi of R phi double of R at this here case, that should be not equal to 1. Suppose it's larger than 1 at the C0. At the C. Then the enclosed volume. Suppose now this equal to, because it's embedded, so that is you have of this of omega, so that is of epsilon of C, that's omega of epsilon, and this of course is C equal to the ball. Sum of radius of R0. The enclosed volume of this omega, so of course surface area same because it's same complete same metric. So enclosed volume of omega epsilon is larger than the volume of omega 0. So in other words, isometric inequality, suppose holds is the optimal case is not a slice. That's the legacy class. You see the volume is larger than this. The area of the boundary of this guy equal to area of boundary omega 0. But the volume is increasing. Usually, sorry, what I'm doing. So volume decreasing. No. Did I do something right? No. So originally same. So we have same area. Suppose now volume is the smallest one. Okay, yeah, that's right. So just violate the isometric inequality. So that's the region you have. Suppose you have that. But now let me look at the other way around. Suppose now this is true. But now put assumption this is also true. Okay, so that's, suppose this is true, then I walk by Jingfang Li and Mu Tao Wang and myself, say that in this case, then the optimal and body realize isometric inequality is a slice. So that's a different. So in other words, then the volume. Suppose okay, let me just say that. So if boundary of omega equal to boundary of V of the slice of R, then the volume of omega will be larger than equal to volume. So there are many things very interesting here related to this so-called warp potential. Warp potentials and give some region are forbidden region. You cannot do much about it. Some region are very nice region. All those inequality will be nice and established. So this also related to the actual dimension quality. So finally, I want to mention this open problem. That's originally we want to look at, but we are still not able to do anything about that. Is the space, the warp apart space with horizon. With the horizon, that means then these are 0 positive and phi times 0 is this. Okay, in particular, say anti-deceptive space and so on. You have a horizon, that means that so this of R0 things are not defined. And outside, and you have of this metric. The question, so in particular in anti-Schwarz space, the question, can you embed, say, S2G into this type of space? Instead of R3 just looking at this space. But this space, of course, you take and R go to 0. For the anti-difference space, get to the space form. So the more or less you want to do a certain kind of perturbation, and this, of course, and in the very natural space. But still, we are able to do that. You can always embed it, no problem, outside of the horizon. But the question, can you embed this contained horizon? It turns out that the problem is not about estimate, not about openness. The problem is about the homotopic path. You cannot start from 0, t equal to 0, because you want to have, of course, you want to have, the path has ellipticity because you want to solve elliptic equation. Suppose now you can do something at t0, you will get contradiction. So the problem is related to called the existence of homotopic path. Because you cannot start from 0. The question, what can you do? Of course, the question probably you want to do from outside instead of fixed one, somewhere, somehow. So this also poses another question. Because even for the classical Weyl problem, so far, basically it's matter of continuity. So nowadays, so many, geometric flow and so on, use these flow methods to produce solution. It's not clear. Maybe the problem also may be ill-posed. So the question then, can we just go outside of method of continuity, do something about the existence? And that's the typical case. Then just look at the anti-dissocial space, see somehow you can create something coming from outside, but you don't want to touch horizon. So that's horizon causes you trouble. So that is not clear. So there are still many very interesting questions related to the mystery of geometric inequality and the regularity estimate. I'll stop here. Thank you.
Any problem? Not the last time. Peng Fei Guan again.
Yeah, the last, actually, we went close by. You can try. You go out, turn right, and go down to let's record it.
Oh, you've been